wave speed is absolute value of u plus square root of density g. So, okay, so let's if I add a little bit more dissipation, does it work? Just seems a lot of dispersion error creeping up without ever dissipated. So let's see. Let me open up the code I did last year to see if I see any major differences. So that's the shallow water equation code I had last year. I had the average plus the new interface. That's the numerical dissipation I had, and it's the absolute value of v plus square root of gh. And v is the same as this, which is u. See any differences? Okay, so let me go through this piece of code. So this is the same, and n is the same, my dx is the same. So I set the h to be the first n variables in the solution, and v to be the last n variables of the solution divided by h. My first flux is h times v for sure. My second flux is hv squared plus h squared divided by 2 times g. And this is the numerical dissipation I'm adding. That's absolute value of v plus square root of gh times dx over 2, right? It's the same. And my new interface is just the maximum over the numerical viscosity from both sides. So the flux on the interface is the average of the fluxes on both sides evaluated in the cell. It's a first order code, plus the numerical dissipation times the difference in the h's. Yeah, the second flux is the average of the fluxes times the the same new interface times the difference in the U2s, which is h times v, which is the solution, which is the conserved variables. And here I'm just setting the interface, I'm setting the boundary fluxes to 0 at both ends, and the boundary flux to h squared over 2 times g on both ends.
For the new code, did you say the flux is the same? Whereas here u should be 0 at both ends, so that's why the first term of the magnetic flux drops out. But here you don't have that first term h times u.
Oh, in the boundary condition here. So if I this boundary is basically setting the first the first one to 0. But it doesn't look like it's an even if I set it to periodic boundary condition, it doesn't quite work. Look again. W.
Is there over 2 missing in your dissipation term?
Is there over 2 in my dissipation? Yeah. So previous in this code, I had over 2 in the dissipation term because the nu is equal to the absolute value to the wave speed times dx over 2.
Yeah.
Right. So here I just got rid of it, but like I previously had a divide by 2 over here, and seems to have the same effect. Okay, so let's actually just make sure we don't have this stuff. Let's comment this out, and let's say WPL. Let's actually make it a little bit clearer. So my right state should be from 2 to end. And the left state should be 1 to n minus 1, right? So this is my for the interface. Oh, sorry, that's not what I wanted to do. I also wanted to comment this out, and for an interface, Wi and Wi for the left state of an interface should be W from 1 to n minus 1 if we are stick to a first order scheme. The right state for an interface should be W2 to end, right? Okay, and let's just it's interface. So this is now we have n minus 1 interfaces because we are only considering the interfaces in the middle. So my FPL is this times UL, and this looks like the same. And my wave speed, the left is equal to this plus this. And I have a maximum flux averaged out plus the numerical dissipation times this. So instead of FR, I'll just have F interface. Yeah, right. W. Yeah, let me just say WIL. UL WIL. Oh, actually, WIL and WIR is equal to that, and I have the average of the fluxes on left and right plus the numerical dissipation. So I'll get rid of all of these and just say that flux interface is equal to, what I'm going to do is I'm going to overwrite the first row as this, and Fi, and the last row as that. So dw dt is going to be fi on the left minus fi on the right, right? So this seems to be very consistent with what we have been doing so far. Okay, so let's actually try this again.